3.
Lasers have been developed very rapidly over the last 20 years or so, and they certainly prove to be versatile. Engineers use them for precision welding and also for cutting. They enable us to produce three-dimensional photos, and each piece retains the complete image, albeit from a restricted point of view. In the home, lasers track video discs. And in hospitals, they're a boon to surgeons. A laser beam provides a kind of sterile knife, literally burning tissue away. Detached retina can be spot welded back into place. Laser beams are so fine that they can be used to eliminate individual cells, or even parts of cells. The list of applications is almost endless. But what's so special about laser light, and how do lasers work? Well, in this program we're going to try to answer those questions to shed some light on lasers. This is a helium neon laser, and the most obvious thing about the light coming out of the end of it is that it's directional. If I shine it on my hand here, it may look rather wide, but in fact the central beam's only about 1 millimetre wide, just that my hand's reflecting rather a lot. Now, if I shine it way down the studio onto that white chair, there you can see the beam's hardly diverged at all. But what about the colour of the light? How can we analyse that? Well, first, let's look at something more familiar. This is an ordinary tungsten filament bulb. And I've mounted it so that the filament's vertical. Now, apparently, it gives out white light. But if we pass it through this diffraction grating, I'll put it up there by the camera, and rotate this filament, then light of different wavelengths will be diffracted by different angles, and we can pick up that light in the camera. Well, what do we see then? Well, there we are. It's a continuous spectrum. It consists of all the colours of the rainbow. So this apparently white light actually has a continuous range of frequencies or wavelengths. Okay, if we try the same experiment with the laser, we get a completely different result. Let's line it up. There we are. It's not a continuous spectrum this time, it's a dot of just one colour. So the light coming out of the front of this laser has a very well-defined wavelength, and if we measured it, we'd find that it's 632.8 nanometers in the red part of the electromagnetic spectrum. Well, before we can understand how a laser like this works, we have to go back to first principles, look at what's going on at the atomic level inside. We need to look at atomic transitions in general. Suppose an atom is in a low energy state, separated from a higher energy state by energy delta E. To make the transition to the higher energy state, the atom has to absorb exactly this amount of energy by, say, absorbing a photon of radiation. The Planck-Einstein formula tells us that the frequency of the radiation must be delta E divided by Planck's constant h. The photon's absorbed by the atom, which makes the transition. This is just the process of absorption. But what happens when the atom is already in the higher energy state? It's only a matter of time before it returns to its lower energy state and loses energy delta E. The most obvious way it can do that is by spontaneously making the transition, giving off a photon of radiation with a frequency again given by delta E divided by Planck's constant. This process is called spontaneous emission. It's an entirely random process. We can't predict exactly when it will happen or the direction in which the photon will be emitted. But there's another way the atom can make the transition to the low energy state. Einstein suggested that if an atom is in a high energy state, it may be possible to stimulate it into losing energy. Well, here's our excited atom, and if radiation comes in with exactly the right frequency, delta E divided by h, then it can interact with the atom and stimulate it to make an immediate transition to the lower energy state, way down there. Well, the atom itself emits a photon, that travels in exactly the same direction as the photon that did the stimulating. So we end up with two photons emerging from the atom. This process is called stimulated emission. The stimulating frequency is exactly the same as the frequency of the radiation leaving the atom. And this radiation has another important property, because if it goes on to stimulate more high-energy atoms into the lower energy state, we end up with a completely coherent beam of radiation. The radiation's in step, or in phase as we say. Now, coming back to the original emission process here, really we're getting two photons for the price of the one that we put in originally. So, in a sense, this is a kind of amplification process. And it's that idea that lies behind the design of the laser. In fact, the word laser is really just an acronym for light amplification by the stimulated emission of radiation.
The first laser that was developed in 1960 was the Ruby laser. And since we use a Ruby laser in our research here at Walton Hall, we thought this would be a good chance to show you just how one works. Now, the heart of this laser is a rod of synthetic ruby like this. And synthetic it may be, yet it still costs several £1,000s for a rod this size. Now, from what you've learnt so far, you know that in order to produce lasing action in the ruby rod, I've got to stimulate emission. Yet, if I just shine torchlight onto the rod, you don't see stimulated emission coming out all over the place. In fact, all you do see is absorption. White light in, and only the pink light gets through. So, why is that? Well, it's because stimulated emission means I've got to force atoms from an upper state into a lower state. And that presupposes I've got the atoms in the upper state to begin with. But of course, matter doesn't normally like to be in an upper state. It prefers to be in its lowest energy state, in its ground state. We talk about the ground state being the one that's populated. And that's why you saw absorption when I shone the light into the ruby rod. The energy was pushing the atoms upwards, the only way they could go. If I'm going to get more emission than absorption, a net emission effect, then what I've got to do is I've got to invert the normal population. In the jargon, I've got to produce a population inversion. And that's where the design of this laser comes in. If I open up the cavity, you can see that here I've got a ruby rod, and down here, although it's very difficult to see because it's colourless, I've got a xenon flash lamp. Now, it's just like the flash lamp that you get in an ordinary camera, just rather more powerful. And it's this I'm going to use to pump the atoms into the upper state in the ruby rod. And perhaps you can also see that both the rod and the lamp are covered with a sleeve of glass. And through this sleeve, I'm pumping cooling water so that the temperature doesn't get too high. Of course, the most obvious thing in here is the mirror surface. It's the mirrors that are causing all the difficulty in allowing us to see exactly what's in the cavity. Nevertheless, it's very useful because, you see, the shape of the cavity is elliptical. And the ruby rod is at one focus of the ellipse, whereas the flash lamp is positioned at the other focus of the ellipse. And it's a property of ellipses that any light coming away from the flash lamp at one focus, no matter what direction it comes in, will hit the silvered walls and will be bounced back onto the ruby rod. So all along the length of the cavity, light will be concentrated from the lamp onto the rod. How is this whole thing powered? Well, it's powered through these cables which feed into the lamp, and the cables go back into this power unit here. Now, all this power unit is a stack of capacitors which we charge up to a very high voltage, actually about 2,500 volts. So the total energy stored in this stack of capacitors is about 5 kilojoules, 5,000 joules. The xenon in the flash lamp is normally non-conducting, but what we do is we trigger the laser by putting a very high voltage pulse on the cables, about 30,000 volts, and that ionizes the xenon gas. And of course, it then becomes highly conducting. So the whole of the energy in this capacitor stack discharges through the cables in about 1 millisecond, producing a intense flash of light. Let's see what happens. I put in the path of the beam a target. It's actually just a piece of unused Polaroid film, and I can charge up the laser now. It takes a few seconds for it to get up to the 2,500 volts. Coming up now, and it's charged, so I'm ready to fire the laser. I'll count down. 3, 2, 1.
Well, it certainly works. But what exactly is going on inside the ruby rod when the laser fires? Ruby is really just an impure form of aluminium oxide, containing a relatively small number of chromium ions. But it's those chromium ions that are responsible for the lasing action and for ruby's reddish colour. Well, here are some of the lowest energy states of the chromium ions. And I want you to keep in mind that these dots represent the chromium ions themselves and not the electrons that they contain. Now here, all 6 ions have their lowest possible energy. They're all in the ground state. Well, as you've seen already, to get the ruby to laze, we have to pump it with intense white light. Now the photons of this light have a wide range of energies, and those energies are just right to excite some of those ground state ions into these excited states up here. Well, you might think that the excited ions will all spontaneously drop back to the ground state. Well, that does happen, but there's another route they can take. It turns out there's another state here, and the ions can decay into that one too. Now that's a very unusual state, because when chromium ions occupy it, they normally spend a comparatively long time in it, thousands of times longer than they normally spend in these excited states here. Now the chromium ions have built up in that excited state over there. So at this stage, there are more excited ions there than there are in the ground state. So we have a population inversion. Now in this schematic diagram, we've only shown 4 chromium ions in that state, but really, of course, there'll be many, many more. So if some of those other ions in that state spontaneously make transitions to the ground state, then the photons they emit will have exactly the right energy, either to be absorbed by these ground state ions, or more likely to stimulate the excited ions to make an immediate transition to the ground state, emitting a coherent burst of radiation with an extremely well-defined wavelength determined by this spacing. Well, don't forget that because the population of that state was higher than the population of the ground state, we'll get more stimulated emission than absorption. So overall then, we've got light amplification by the stimulated emission of radiation, a ruby laser. Now one drawback with this type of laser is that to produce a population inversion with respect to this highly populated ground state, we have to put in a huge amount of energy, enough energy to put more than half of the ions into that excited state. Now normally we can only provide that sort of energy in short bursts, and that's why the ruby laser only gives out light in pulses.
3, 2, 1.
But of course the helium neon laser gives out light continuously. So how does that one work? This is a simplified energy state diagram showing 3 energy states of just the neon gas in the laser. Well, these atoms are normally in their ground states, but we aim to produce a population inversion with respect to this vacant state here. And that should be quite easy, because even if we could excite one atom into this state at the top, then we'd have the population inversion we want. Now, these neon atoms are excited not by light energy this time, but by energy transferred to them in collisions with fast-moving helium atoms. And it's those helium atoms that provide just enough energy to excite those neon atoms into this top state here. So now you see we've easily produced the population inversion we want. So the conditions are just right to stimulate the neon atoms down to the middle state, giving off a burst of coherent radiation. Once again, we have light amplification by the stimulated emission of radiation, a helium neon laser this time. And this process can go on continuously. These atoms decay back to the ground state, and we pump them up again, ready for more stimulated emission. All we have to do is keep supplying the helium neon gas with energy. Here's a helium neon laser. We've mounted it vertically and we've taken the cover off so that we can see what's going on inside. The energy is being supplied to the helium neon gas in here by electricity from the mains. Now let's have a look at the light coming out of the side using the diffraction grating. Camera's in position. Let's put the grating up close to it. There we are. It's a beautiful spectrum. It's certainly not pure laser light with a well-defined wavelength. In fact, what we're seeing here is the spontaneous emission spectrum of the helium neon gas in the tube. The stimulated emission, the laser light, is coming out of the end. How can we understand that? Well, imagine we have a box containing some excited substance. For example, it could be a mixture of helium and neon gas or a block of ruby. There'd be spontaneous and stimulated transitions going on all the time, and radiation will be emitted in every possible direction. The problem is that after relatively few stimulated emissions, the photons will leave the active medium. One way to increase the amount of stimulated emission would be to increase the size of the medium. If we lengthen it, we increase the number of stimulated emission processes in the horizontal direction. So it's only in that direction that the coherent radiation builds up. To produce a really highly directional beam, we could use an extremely long tube, but that's not a very neat way of solving the problem. There's a much better solution available. Suppose we put a perpendicular mirror at each end of the box. The radiation will then be reflected back and forth, re-stimulating the same active medium in between. Obviously, if both mirrors were perfectly reflecting, the beam would never escape. There's a way out though. We make the mirror at one end only partially reflecting.
This is the partially silvered mirror, and of course that's been highly accurately aligned with the fully reflecting mirror at the other end of the cavity, with the result that the output beam is highly directional. Now, so far I've not said anything about the output. Of course, it's a pulse laser, so we'd really like to know what that pulse looks like, that is, how its intensity varies with time. Well, we can do that with the photodetector here. This is a photodiode which uses the photoelectric effect to convert the optical signal into an electrical signal. And the electrical signal is passed down the cable into the oscilloscope here, and because it's a pulse, I'm taking a photograph of the oscilloscope trace. So let me arm the camera. Okay, and now charge up the laser, and it's charging, and it's coming up to the 2,500 volts now. So 3, 2, 1, fire. Okay, let's see what we've got. Pull out the photograph, throw the old one away. It takes a few seconds for this to develop. Tear it off. And yes, what I've got is a rather complicated trace. This is 0.2 milliseconds a centimetre across here, so the whole width of the pulse is about a millisecond. And if I show you the trace of the flash lamp, the lamp pumping the laser by itself, I took this earlier on, you can see that the profile of the laser follows much the profile of the flash lamp. It's about the same. The spikes are really rather more difficult to explain, but don't forget that the ruby rod is not uniformly illuminated by the flash lamp, so different parts of the rod will get to their population inversion conditions at different times, so it won't laze completely uniformly. Now, unfortunately, the laser pulse we've got here is not ideal for doing the sort of research we're interested in. See, we're looking at the excited state of organic molecules and dyes, things like benzene and its derivatives. The problem there is that if we're going to attempt to find out about these excited states, the lifetime of the states is of the order of 100 nanoseconds or so. So when we probe it with laser light, we want to be able to probe it with a pulse which is much shorter than 100 nanoseconds. Now, fortunately, with just a little bit of modification, we can get our ruby laser to do exactly that. You see, remember that it's the optical cavity that allows the avalanche process to build up. If I block off the cavity with my hand, then I get no lasing action. But suppose I block the cavity off not with my hand, but with a special dye. This dye has a slight greeny tinge to it because it absorbs red light very strongly. And of course it's red light that the laser's producing. So when I put this in the cavity, what now happens is that the flash lamp fires, builds up the population inversion condition, it attempts to laze, so there's spontaneous and stimulated emission, a little bit of it coming out of the end of the ruby rod here, tries to get to the mirror, but gets absorbed by the dye itself. Now, just think what absorption means. It means that molecules in the low state are going to be pumped into the upper state. If I now adjust the concentration of the dye so that the flash lamp is at its peak, the population inversion conditions at a maximum, just when all the molecules are being pumped into the upper level, then there's nothing left in the lower level to absorb, which means that to all intents and purposes, the dye becomes transparent. So what now happens, of course, is that the laser light can get through to the mirror. There's this huge rapid avalanche build-up, a big pulse of light coming out at the end. The population goes back down to the ground state in the ruby rod. The molecules in the dye fall back down to the ground state and switch the whole thing off. In fact, this technique is known as Q switching. And the result is that I produce a pulse which is now much, much shorter than before. This is on a time scale of 50 nanoseconds per centimeter, and you can see that the pulse width is typically of the order of half that, 20 nanoseconds or so. And better still, I get a lot more power out of this system now, because a large percentage of that energy, which I previously had in the millisecond pulse, has been stored in the ruby rod and now comes out in the 20 nanosecond pulse. So let's see what that does to our target. I'm positioning it just a little bit lower down now so you can compare it with the previous un-Q switch pulse. We charge up the laser unit again. And it's charging, it's coming up to the 2.5 kilovolts now. So 3, 2, 1. Well, pretty impressive. That's 200 megawatts. And what's more, that was all done with a parallel beam, a beam which is not diverging. If I put a lens in the path of the beam, then what happens now is that the laser light is focused down to a point which is going to be at the focal point of the lens. It's in this case about 3 centimeters behind the lens. Now the power density at this point will be so high that it will be able to rip the electrons off the air molecules. It'll ionize the air, and in this point here, hopefully we'll see a ball of lightning. So let me see if I can really impress you this time. I think we'll take the lights down and I'll charge up the laser again. The laser's charging. Don't forget, look just to the right of the lens. 3, 2, 1.
Well, Q switching certainly does allow us to increase tremendously the power delivered by our ruby laser. Well, in this program we've concentrated on ruby lasers and on lasers containing helium-neon gas. But nowadays scientists have found that almost anything will laze, and there are now chemical dye lasers in which we can actually adjust the output wavelength. But perhaps what's most impressive these days is the range of power outputs available, from this microwatt laser the size of a pinhead right up to this monster, the Shiva laser used for nuclear fusion research in the United States. Its output is astonishing. It's 200,000 times more powerful than our Q-switched ruby laser.